afternoon, everyone. So I shout. Yeah, welcome to this webinar, Friday afternoon, as usual. And today our speaker is Latévi Lawson. Yeah, Latévi studied theoretical physics at the Institute of Mathematics and Physical Sciences in Benin. Yeah. And after that, he became assistant lecturer in physics in Togo at the University of Lomé. And since 2020, he's at Ames in Ghana. Yeah? And Latévi, thank you very much for offering to give a talk. I see you already shared your screen. You're welcome to start. Thank you very much.
Yeah, thank you very much for this opportunity to give a talk here. So I would like to, I'm Francophone, so excuse me for my Francophone accent and for some of misspelling word during these presentations. And I would like to thank, first of all, some of you who work in the shadow to make this presentation possible. I mean, Rene Cose, Dr. Pleasant, and Chanel, and Professor Francesco Petrogioni. So it's an honor for me to present in this seminar. So I will say that I'm currently postdoc in at African Institute for Mathematical Science, where we are focusing on the fault-tolerant topological quantum computing and quantum algorithm optimization. So this work is our first result for this position, and is done in collaboration with Prince Osei, Dr. Prince Osei, the center president of the AIMS Ghana. And for those who are not familiar for this talk, it will be a little bit technical, but I will try my best to clarify all the points. Can you hear me? Okay, to clarify all the points in this one. So, what is about this topic, encoding topological qubit using Higher lattice gauge theory model? It just we try to create uh, high dimensional topological qubit based on the lattice model using a techniques of gauge theory. Okay, so it's what is we are going to tell about in this presentation. So I would like to thank some of founder that provide the grant for this study. I mean, AIMS Research Center for Innovation and AIMS Ghana and Quantum List Africa. So I'll start my presentation with this beautiful picture which have made a buzz on the internet. This is a Microsoft quantum processor which encodes topological qubit. You know, there is a challenge among the big tech like IBM, Google, and the Microsoft to be the first company to create the first quantum computer. So each of these enterprises or for this industry using different approach. For Microsoft, he introduced this one on the February 20th of this year. He put this one, he create a kind of quantum processor that encodes at least 8 topological qubits for which is a big achievement, but it's not yet the state to processing the quantum computing because you have to cool also at the low temperature this device. This is what Microsoft did, which is a big achievement to show that this approach of quantum topological quantum computing is also a candidate for the next generation of quantum computing. So, for the purpose of this talk is to encode quantum information, or I mean, is to store information. And so, since we are in quantum mechanics to store information, the space where the information will be stored is the Hilbert space. And we are going to consider a subspace of this Hilbert space that we call the protected space or the encoding space. This space is defined like this. We have a vector which will be considered later by the ground state, is such as that this operator leave the action of this operator on this vector leave this state invariant. Is what we mean by encoding the information and the ground state. Okay, so all the information or the ground state that bear the information will be bear by this operator. If you look in ordinary quantum mechanics, the ground state is a wave function, but in this current state, the ground state, the information on the ground state will be bear by this operator, which is the projector operator. Once we code in the information, the next point is to show that this is, information is stable against all the perturbation that can happen in the system. So here we will define an operator Ti, which is will be the different type of the transformation in my system. And at the end of the day, I have to show that all this transformation let the projector, the ground state projector invariant, and let the the uh, the scalar product also invariant. Is that is the target of my the talk. So let's start by the motivation. We know if you are hearing my voice now is due to the classical bit, which is the small fundamental entity to code the information that we call by a bit, is either 0 and 1 to encode the classical information. But now we are looking for quantum information or quantum bit, which is the superposition of the 0 and 1. Because if you superpose these two bits, it gives a lot of advantage, like the super faster of the algorithm. And for many computation that will take a decades of year for this superposition and with the integrament of the quantum world, we can run this computation at second. Now, once we have this, we store the information. The next point before our classical computing is to process this information. Here we have, for example, the initial state, we have the input of the information that we can see here. This is the device. And at the end, we are looking for this output, which is the Y, which is the measurement here. So here we have a kind of device, which it can be the transistor and all those that we call the logic gate. So all these materials is inside of our computers. Now, this technology, we want to have it also in the quantum version. We are looking for the same architecture in the quantum version. So we have the initialization of our quantum state, and we are looking for the output, which is be the measurement. And to get the output is through what we call the quantum gate, which is a unitarity operators. So for the current state, the device to implement all those architecture is look like this, because we are still at the beginning of the quantum mechanics, and the law, the Moore law is not yet applied. Once we know more about this one, we can reduce the size of all those things. Now, the big problem with the quantum computing is the decoherence. Uh, our qubits that we are using are very fragile when they interact with the environment. Either, for example, if I have the qubit 1 here in front of or in contact with the environment, which can be the noise or the perturbation, is flipped to this one, or we have the phase flip. Now, how this is the only problem that you have today to achieve the next generation of the quantum computer. Now, how to solve the problem of decoherence that introduce error in the computation? We have the first approach based on the software approach, which is error correction code, and we have the hardware approach using the topological order of the matter. Now, what is topology? Topology is a concept in mathematics that is very wonderful concept. Before understanding topology, is very important to understand what we mean by geometry. Look at this figure. We have the cycle, we have the square, we have the triangle. In the geometrical framework, these are different because geometry design object by the metric. I mean, by the distance or by the length. So in terms of distance, these three figures are different. But in the topological framework, the cycle is equivalent to the square, is equivalent to the triangle. It means that we can deform the cycle to a square and the square to the triangle. It's what we call by topology. So the topology is the property of the object of the space to be invariant or to be conserved under a continuous deformation of the space. So the most popular one that we know from the literature is the equivalence between the donut and the tea coffee. So this is what we are going to use to store in the information. So if we come to the physics, okay, we have some organization of the some particular some particle in the matter uh, exhibiting some topological properties of the matter. Like we can have here a particular type of the particle, which are exotic particle we call by anion. Okay, and the anion have some topological order or some topological properties that is going to be used for encoding the information. You know, the we are going to focus on the non-abelian anion. Okay, so because the difference between the different kind of approaches is the use of different type of the particle. For the topological one, we are going to use non-abelian anion. Like to process the information for the anion, we create the vacuum, which is the creation of the anion. Now to process this anion, we create what we call the topological quantum gate, which consists of braiding this anion, and at the end of the point, we have the measurement, which consists of fusing the anion. So this is the schema, or this is the figure that show all things that I have described above. I have here how to create the memory or where the information is stored, and later we process them by braiding them. At the end, we have the fusion. So in this type of work, we have three types. We have those researchers that are focusing and creating the memory, store the information. Those are focusing the braiding, and others are focusing in the fusion. For my talk of today, I'm going to focus in only on how to encode, how to create the memory to store all those qubits, because the mathematical tool to describe them are different. So the question is how to encode the political qubit. Thanks to Kitaev, who was the first who proposed a model, he considered a topological manifold in which is embedded a lattice model. We have the set of the vertices, we have the set of the edges, the set of the face. So all this structure is embedded in a topological manifold. Here, he considered a torus. The reason to choose the torus here is because of the torus present non-trivial topology, and we have in the rest of the first part of the work, we are going to focus more on the structure and leave the nature of the topology. In the Kitaev model, the particle will move only through the edges here, and we leave the vertex and the face empty. We don't touch it. So the mathematical tool that Kitaev used to describe them is called quantum double, based on the quantum algebra. Later, people find that we can look Kitaev model in the lens of what we call a gauge theory. What is gauge theory? Gauge theory is just a map between a mathematical object and the physical object. It's a way to assign mathematical object to the physical object. In the Kitaev model, we are going to assign the group which describe the symmetry of the system to a lattice, a two-dimensional lattice. So here we have, so we are going to symmetrize this lattice. We leave the vertex, which is the face point blue here, intact, and the face also intact here. It's only the edge that bear the information that design the circulation of the particle in my graph here. So the first point is to look for what is the Hilbert space representation of this graph. and the second to look at the emission product and the orthogonality. From this representation, we define the Hamiltonian model, which is described on this form. The question is, we know Hamiltonian formulation in the ordinary quantum mechanics, which consists of the kinetic part and the potential part. We can see that the same architecture here appear. Okay, so ask me at the end of this talk, what does it mean, the correspondence between this formula with the one that we have. Once we have the Hamiltonian, we can create the protected space, which is defined like this. Here the operator P is defined like this, and leave this ground state invariant. It's what we call by protecting the information or encode the information in the Kitaev model. Now, in our case, we are going to generalize the Kitaev model using the representation of two groups, okay? And the lattice is will be in three dimensions. We call this gauge theory higher gauge theory. It means that we are going to symmetrize the edges and also the phases, okay? And we consider the third dimension, which is given by the cube. All this cube is rely on this face, okay? The question is how to construct the Hilbert space, how to define the Hamiltonian model, and how to define the ground state. We are going to use approach of Kitaev. So to do this one, I will follow the plan. First of all, I have to explain the boring part of this presentation, which is the representation of two groups. And the second point is to encode, to assign this two group to a lattice model and to what we call by higher gauge theory. In gauge theory, we have four fundamental ingredients, which is the matter field, which is represented by the lattice. We have the gauge configuration, gauge transformation, and gauge invariance. And from all those ingredients, we will encode them in the Hamiltonian, define the ground state, and show that this ground state is invariant against all the perturbation in the system. So in the representation theory, we start by representation of one group. Representation is a homomorphism from the group to the group of the from the vector space, and we can see that it keep the structure and transform the identity of the group like this. And once we have defined the representation, we define what we mean by the equivalence between two representations. Okay, so to show that two representations are equivalent is to define an operator or this transformation that satisfies this intertwinal relations. So the very important point when you are studying the representation is to look for the irreducible representation. But in the present case, we stop here because we look for the encoding. When we are going to study the excitation or the dynamic, how to process the information, the the use of the unitarity is very important. But in the present case, we look the representation and the transformation from one representation to the other one. So this representation can of the group in the vector space can be looked in the language of the category. So the representation in the language of the category is a functor, okay? It's a functor from the category of the vector space to the other one and satisfy these properties, okay? Which is look like the same because the group itself will be like a category, one category where G0 is the state of the object, J1 is the state of the one morphism in my system. So we have the interlinear relation with design here, the natural transformation. If I do have two representation, I will define what we call by the natural transformation, which respect this interlinear relation. So there is a graph that shows that this one, but I skip it. Now I come to the two group. The two group is a generalization of one group. So there is a three equivalent definition of the true group. True group can be defined like a true groupoid, and the true groupoid is a true category where all the morphisms are invertible. We have the set of objects where we have the S here is an object, and we have the one morphism is the applications that link the object of the set of objects, okay? And we have the second two morphisms that link the one morphism each other, which is given by alpha. We have ST, all those map, which is some composition map, which is well known in the literature. I'm not going to define them here. I send you to some literature to look how these maps are defined. S means the source and the target of the category. So the second approach to define the two group is to define them as a cross module of group. So we consider two group E and J, and we consider two map. The first map is a group homomorphism from E to J. It means that it keeps the structure of the element of E and transform the identity of the E to the identity of J. And the second map is the left action of the group J on E by automorphism and satisfy these properties. And now we have the third relation, which is the compatibility with the homomorphism and the left action, which is given by the perfect relation. This is the second way to define a true group by means of the cross module. The third approach is to define the true group as a cross module over a groupoid. It means that we define here a category associated to the first to the cross module. We have the set of objects here. We have the set of one morphism which represents the J, and we have the set of two morphisms which is the semi-direct product between the J and E. It can be represented in this form, okay, with additional properties. Now, the representation of two group here will be considered like a two factor between the category of the cross module and the category of and two groupoid. Okay, such as that, it satisfies this relation. We have the representation of one morphism is given by this relation like this. It transforms one groupoid by the action of this operator to something like that. For the two morphism representation is given by this relation. I have two morphism here, which is transformed through the representation of cross category of cross module and give me this output. So one point about the category is to study the composition law, how the morphisms are combined. We have the composition of one morphism is given by this relation, and we have the identity of the morphism also given by the relation. We have concerning the two morphisms, we have two types of the composition. We have the vertical composition, where we have two categories. We can compose them vertical and give this one, and this is the identity of them, of this category. And we have also horizontal composition. We have this category, two category, and I have this one. I can compose them horizontally and give me these things, okay? And the third point, and the composition of two morphisms and one morphism that we call a whisked. We have the left-right whisked here, where I have one morphism composed with the right morphism. Two morphisms is giving me this output. And I have also the left whisked representation, which is the composition of two morphisms and one morphism is given. This briefly summarize what about the mathematical part of the category. Now, once we define the representation of category, we are going to define a pseudo transformation, how to transform two factor to the another one. Is given by this diagram, and this diagram should be commute and give me this relation, interterminal relation, which generalize the natural transformation. Now, this is the boring part of this presentation to describe the mathematical tool that I'm going to use. Now, this mathematical tool will be assigned to a lattice model, a physical model, which is a lattice, here through a model that we call by through a lattice, through a gauge theory. Okay. Now, here is our model, the lattice model, which is we consider the manifold, topological manifold, in which is embedded this lattice model. We consider this lattice in 3 dimensions. We have the 2 dimension and the third dimension, which is the cube here. We have L0, the set of vertices, L1, the set of edges, L2, the set of phase, okay, or we call it the placket, and the L3 is the set of blob, which is the volume, okay. The third dimension is given by this element. Now, the second point, once we design our lattice, the second point is to dress the lattice. This is a very important point of my talk. Now, dressing the lattice means that to fix some regulations, to fix some point, this dressing may be different to another dressing. So at the beginning, I fix the base point of this lattice. Here, I take a symbol of this lattice, okay? I consider this square. This is the fixed point on which all the placket is rely on. Now, the second point is to ordering the vertex. Like the vertex alpha, the base point is smaller than the vertex V1, V2, and so on. The third point is to orientate the edges, okay? Like I can see the edge here move from the smallest vertex to the bigger vertex, okay? And the third point is to orientate the placket. We can orientate the placket in the clockwise or the anti-clockwise. For my case, I will choose to orientate the particle to move in the anti-clockwise rotation. This is what I'm going to consider through my talk. Okay, once I change one of these dressing, I change configuration of my system. The second point is to define what we mean by gauge configuration. The gauge configuration is now to assign the representation that I define to the lattice. So for the lattice, I assign path groupoid because path groupoid is also a groupoid. The only thing is here, I have, instead of considering the edge, I will consider the path, the the uh, the the multitude edge that will form the path. Okay, and I represent them like this. After action of the representation, I have this configuration of my lattice in D form, and this is how I design my configuration. So the lattice now I have on the edges the representation of the edge. In the blue, the face now also is represented by another representative different from this one. And the third dimension also look like this. This generalize what Kitaev have done. Now, what I'm going to define now the gauge transformation. To define the gauge transformations, it's very important to define how my Ibet space look here. The Ibet space representation is the composition of the edge representation here and the face representation here. This is the way we define the Ibet space representation. I define the emission product, which is the scalar product defined by the relation 4, and the orthogonality is defined by the relation 5. And once we have our Ibet space, is to define the next point, the gauge transform. The gauge transform is just an operators that add from the Ibet space to the other one. We define two types of the operator. We have the operator that we call the vertex operator that add from the vertex by this action of element of the group. So if I consider the vertex operator acting on the edge representation, when the V, the vertex is the starting point of the edge, I can see that this representation is translated by H. But if V is the endpoint of the edge, gamma is inversely translated. Otherwise, it keeps the representation intact. Now, for the first representation is the way the vertex representation acts. If the vertex, the target vertex is equal to the base point, we have this expression. Now look at some example. I consider this graph here with all the representation. Now I'm going to add this operator from the base point. I can see that all the adjacent edges here are the starting at the end point of this vertex. I can see that is translated by H and this one. And since this vertex is acting from the vertex, the base point here, I have the action on the phase representation. I take another action. Now I choose to add the operator from the V2. Okay. Now I can see that the V2 is the endpoint of this vertex and the starting point of these edges. So we can see that since this one is inversely translate this representation and translate these edges by this representation. Now it leaves the phase intact invariant because V2 is different to the V alpha. Now, from this representation or from this action, I can have this. The first result is given by the relation 9. If the action is from the same vertex, I have the multiplications of the group element. But if the vertices are different, I can see this. I can see that all those operators commute. Concerning the edges operators, okay, this one is a little bit complicated. Now, I define the operator that act from the edges, okay? So this operator acting on the edge representation is given by this relation when the edge is equal to the edge prime. Otherwise, it leaves the representation intact. Now, for this edge operator acting on the face representation, I get this formula. When the edge aligns with the orientation of the bracket, I have this formula which is here. I will show you by the following example. But when the edge aligns against the orientation of the bracket, I get this formula. This is given here. Otherwise, it leaves the the representation invariant. So this is an example. I will choose here in my the target edges here. I will add this operator gamma 1 3 on these edges. Since this edge is aligned with the orientation of this one, the orientation of the bracket, I can see that okay, here I have the action of this element to this representation, and I have this formula. This is this operator that affect the face representation and give me by the relation like this. Now I take another edges that goes go that align against the orientation of the placket. Right? I can see that here this the target edges is affected by this operator. Okay, now since it's going against the orientation of this one, I have this element that is at. Maybe in the question we can come on it and I will explain you how this action works. So from this edge representation, I have this formula here. If the action is from the same edges, I have the multiplicative of the group element. But if the edges are different, this operator commute. I have in the relation 11 the relation between the vertex operator and the edges operator that is given, and in the 12 formula, I have the second relation that relates the vertex operator to the edge representation. This is what I define by the gauge transformation. So the third point or the last point of the gauge theory is to define the gauge invariant. The gate invariant just means that all the path, all the configuration that invariant in my system. It means we call those elements the holonomy. So we have the holonomy one related to the path when I move the base point, I come back to the same base point. It's defined by the relation 13 that we call the holonomy. Okay. Now this holonomy is constrained by the relation 14. And the second point is to define two holonomy that we call by two fake flag configuration is the collection or the composition of the edge representation and the face representation in my graph. And this holonomy also is constrained by the relation system. This is an example of a graph or a lattice. I have this triangle three sub triangle inside, and which each sub triangle have a representative edges representative and face representation, and I will consider the base point for this lattice or for this lattice V0 and V2. How to compute now this holonomy is given by this relation. If someone want more clarification, I can come back on it to explain how we compute the one holonomy for each sub triangle and the two holonomy for each sub triangle in the big triangle. That is the way we compute the holonomy, which is combinatorial. Now, from this holonomy, we are going to associate an operator that we call the placket operator for the one holonomy is defined like this. And for the two holonomy, we associate an operator that we call the block operator, which is defined in this form. So, like I said, is this operator are invariant. And this invariability is shown by the relation 1718, showing that the action of the edge, the vertex operator, and the edge operator leave this operator invariant. That is interpreted here by the commutation relation of this uh, mm, mm, this relation. Okay, so once we define all the ingredients of our lattice gauge theory, now we are going to gather all this information and put them in a Hamiltonian model. So the Hamiltonian model of this system is defined in this form, this relation 19, which is the collection of the above operators that are defined. Here is the operator for the vertex, the operator for the edges, the placket, and the blob. You can see that is follow the same architecture of the Kitaev and the manuals here, which also it put here. So we can show that this all this operator define a projector operator. It means that when I take the square of this operator, each of this operator is equal to itself. Now, if I take the conjugate transpose of this operator, it leaves it into itself. Is what we call by a projector. Okay, so the projector operator is an operator that is very important in topology to define the invariability. So we looked at our model are defined by the projector operator. So from this representation, now we can construct the ground state of this system. The ground state, like I said, is a source space, which is also called by the protected space, is defined by the relation 20, where all these above projector in the Hamiltonian leave the ground state invariant. We can show by the relation 21 and 22 that the gauge transformation or the gauge the local operator leave this ground state also invariant by defined by the relation 21 and 22. And finally, we define the ground state projector. The ground state projector that code all the information about the ground state is defined by the relation 23. And finally, we define the protected space where the information are encoded. You can see that this projector ground state leave also the ground state invariant. It's what we are looking for this representation. It's what we call by encoding the information by the relation 24. Okay. Now, once we define this one, we are going to show that the information stock is invariant against all the perturbation that can happen in the system. So the perturbation that we define here are T1 is this perturbation or this transformation is a way to transform or to affect our addressing that I defined at the beginning of my system. So the first transformation is what we call the flipping the edge orientation. I have my edges here from V1 to V2. The transformation T1 will flip the orientation of my edges. It's kind of transformation that can happen during my system where the edges, when it's going from the left to the right, now it can be affected by something external phenomenon that orient the orientation from the right to the left. I have the second transformation, which is the placket orientation flipping. It's defined by the relation, by the transformation tool, where I have, at the beginning, I said that I, I choose to orient my placket in the clockwise, anti-clockwise orientation. Now this transformation will inverse the transformation. Now instead of being anti-clockwise orientation, it will be now the clockwise orientation. So this is what about the transformation 2. And the transformation 3 is now to flip or to swap the base point here, the base point V1 to V2. Okay, it's also a kind of changing in my dressing. So if I flip or I change the base point V1 to V alpha 2, I change my dressing. So these things appear in my system. So this is the three kind of the transformation or the perturbation of my lattice that can happen in my system. So from all those transformations, we can get a result from 25 showing that, okay, this transformation are unitary and also is commutative. And here, this is the topological projector. And what I'm going to show as a theorem here is to show that all the above transformations that are defined, flipping the orientation of the edges, flipping the orientation of the placket, and changing the base point, leave this operator 26 invariant. Okay, is what is a long computation. I can show all of this computation here, and also leave the scalar product also invariant. This is what we call unitary and the topological invariance of my lattice. So this is the mathematical approach to stabilize or to make robust a high dimensional qubit. This is a mathematic. Now it's up to now to show if all those things can be satisfied experimentally. This is what we got as a generalization of the Kitaev model. Thank you for my presentation.
Thank you very much.
Hello.
Latévi.
Yeah.
Good. Do we have questions for Latévi? Krishna. It's open to you. Yeah. Any questions or comments?
Can I ask a question?
Yeah, please, you're welcome.
Thanks for this interesting talk. I just would like to ask you, I was wondering, do you see a possible way to couple your 3+1 two group lattice gauge theory model to gravitational degrees of freedom, either semi-classically or in another way?
Okay. Yeah. Uh, I'm not. I'm doing quantum gravity. You know, in quantum gravity, we have different approach, mathematical
Mhm,
approach.
mhm,
Uh, the approach that I use is mostly based on a non-commutative geometry. Is what was about my previous research, but in the case of using two group to describe quantum gravity, I don't know how
No,
it's used.
actually, why I'm asking this question, because as you know that there is some topological case theory which is called the B wedge F theory. So
Yeah,
can
sure.
you generalize this kind of model in a language of the gravitational case theory? In fact, is a topological framework.
Sure. Yeah, it's happened because I recently seen a paper where they use this one to define gauge theory, because everything starts by defining what I
Mm,
mean by my invariant operator. You know, even from here, from what I define here, for the ground state operator. This operator is a topological invariant operator. I can
mm,
relate this one to a quantum field topological field theory, and now starting describing the gravity like quantum gravity like an invariant, a constraint in my system. Okay, it's by following many talk in this area is the way they use the topology quantum field theory to define gravity as a constraint in my system. So they
okay,
use all those approach, but like I said, I'm not too much interested in this approach, but I am more focusing on how to compute, find the fault-tolerant quantum computing.
okay. Thank you. I have another silly question. The
Yeah,
point is, as we know, symmetries in dynamical system are usually described by ordinary one group, say.
yeah,
So often
yeah.
continuous and connected to conservation law via Noether's theorem. So in your framework involving two groups, could you please clarify, are these two group symmetries continuous or discrete? Also, is there any analog of Noether's theorem relating these higher symmetries to conserved quantity in your model?
Okay, thank you for your presentation, your question, because uh, uh, in the literature, what we know, even from
Hmm,
the people use one group.
hmm,
Okay,
hmm,
one group is a way to describe our current state of for the topological qubit. Okay, the symmetrized the topological qubit. Now the two group is a little bit abstract because uh, using
What is
now
what is the
different
representation of two group? I mean, I could not
yeah,
realize actually.
okay, yeah, your question is welcome. Two group in fact is a generation of a one group where it can be defined in a three equivalent way. Okay, a group itself can be look like a category, okay, a one category. Two group is a higher category, okay, and the higher category is described by the small two category. Two group can be defined first of all like a two groupoid, where two groupoid is a two category. I don't know if you know more about the
Mm-hmm,
category theory.
mm-hmm.
Okay, it's a two
But
category where all the morphisms, like one morphism and two morphisms, are bijective. This is the first way to describe the two group. The third way to describe, the second way to describe the two group is to look like a cross module. Cross module is a notion, is a concept introduced in the topological algebraic topology, where we consider two group here, and it must satisfy all those properties that are defined. We can see that you have two additional map here, the way I define it. And the third way to define the two group is to look the cross module over a two groupoid. Is the way, this is the true equivalent way to define the two group. So I can say that there is no appropriate or appropriate definition of two group. So it depends of what we are looking for. Okay. So in my case here, I'm interested in the first equivalent definition of two group and the third equivalent definition of two group. And now my representation here will be defined like a phantom. A phantom is a map between two categories, okay, two equivalent categories. So
mm-hmm,
my map here, the representation here is a two phantom between the category of the cross module to the category of two groupoid is what I define as a two group representation. So in the physical way is to assign this mathematical object to my lattice model, three-dimensional lattice model, one representation to the edges, one representation to the face. This
okay,
works.
okay. So does it indicate?
Pure.
Okay.
Go ahead. Go ahead, please.
I understand. But does it indicate that if you want if you one can generalize this situation 3 plus 1 to 4 plus 1, so then we need three groups.
Yeah, you are right. Yeah. In fact, that is our original, maybe the next point that we are going to do, but it's very, very complicated and maybe very abstract from the physical goal, because the goal is to look for the fault tolerance quantum computing. Even three-dimensional lattice does not exist because the anyons live only in two dimensions.
Mm.
Consider the anion to live in three dimensions is just a mathematical abstraction of what exists. Now going to four dimension, yeah, is abstracting the physical world. It's mathematical beautiful, but physically, at the state of our knowledge, is not very important because we are looking for a fault tolerant quantum computing, how to preserve our qubit from all the perturbation that can happen. But in mathematical framework is very good to look how the four-dimensional topological qubit can be looked using true group. Yeah.
Okay. Thank you.
Okay, Latévi, thank you very much. Is there any other urgent question? Because we have another seminar. Yeah, Latévi, thank you very much for your talk. And
Yeah. Thank you.
we will stay in touch. Yeah.
Yeah. Thank you. Thank you very much for this opportunity to present my talk here. Thank you.
Good pleasure. And you should find it on our YouTube channel tomorrow.
Yeah. Thank you very much. Thank you very much.
We'll send you the link. Yeah.
Yeah.
Thank you very much. Thank you. All
Thank
the
you.
best.
Yeah.
Bye. Bye-bye.
Bye.